Hi, so for today we're going to talk about non-exact DE made exact using integrating factor. And for today's video, I'm going to show you how are we going to make the non-exact DE as an exact DE using the what we call the integrating factor. But before that, I would like you to first make sure that you watched already my video all about exact DE, because in the process of our solving non-exact DE made exact using integrating factor, we're going to solve this as an exact DE later on. Okay? So if you haven't watched my video about exact DE, please watch it first before proceeding with this video. And if you watched it already, thank you so much. And we're going to tackle non-exact DE for today. So in order for us to uh, solve a non-exact DE, we have to familiarize ourselves with these formulas. So for number 1, we have 1 over n. Okay? We have 1 over n multiplied by the partial of m with respect to y minus the partial of n with respect to x, and that is equivalent to f of x. Okay, so the definition of our m here and our n here, okay, is still the same on what we have discussed on the exact DE. Okay, so and here is what we call the integrating factor. The integrating factor is the factor of which if we are going to multiply the non-exact DE by what we call the integrating factor, okay, then upon multiplying the integrating factor on the whole equation, then we will be making the DE exact. Or in other words, integrating factor is the factor of which when multiplied to the whole non-exact DE, then the non-exact DE becomes exact. Okay? So, if we use this formula, 1 over m and multiplied by partial of m with respect to y minus partial of n with respect to x, that is equivalent to f of x, then we must use an integrating factor of this. So IF stands for integrating factor. IF is equals to e raised to the integral of f of x dx, of which our f of x is the result of this. Okay? And for number 2, if we're going to use this formula, 1 over m multiplied by partial of m with respect to y minus partial of n with respect to x is equals to f of y. Then our integrating factor would be a little bit different. E raised to the negative of the integral of f of y dy. Okay? So, the goal for the integrating factor, okay, the goal for the integrating factor is to make it as simple as possible. And, sir, how do I know if I'm going to use number 1 or number 2? If you can express, okay, if you can express the value of f of x or f of y into a what? Into a constant, okay, or into a single variable, okay, that is the formula that you're going to use. Okay, so again, if we are going to use 1 over n, f of x should be a constant number or a constant plus a single variable, but never a 2 variable. Because we will be having a problem if we integrate this into 2 variables, x and y. And so, if we are going to use this, we must, again, come up with an f of y that is a constant or a constant plus a single variable y, of course, f of y, and but never x and y. Okay, so as we go on our discussion, we will see this. Okay, so let us try to solve this one. Okay, recalling from our previous discussion, this is our m, and this should be our n. Okay, so test for exactness. Partial of m with respect to y should be equal to the partial of n with respect to x. So if you get the partial of m with respect to y, we're going to get a derivative of m with respect to y, which is y minus xy. And evidently, we can see that the partial of this with respect to y is 1, because the derivative of y is 1, minus derivative of y is 1, so that should be 1 minus x. Okay? And the same thing, if we're going to get the partial of n with respect to x, that is partial derivative with respect to x of this n function, we have x. So that is equivalent to 1. Therefore, this partial of m with respect to y is not equal with partial of n with respect to x. Therefore, it is not exact. It's not exact. Okay? And so, sir, we will be using the formula here, okay, to get the integrating factor, of which if multiplied to the whole equation here would make the DE exact. Okay, so let's try the formula number 1. So the formula number 1 states that 1 over n partial of m with respect to y minus partial of n with respect to x is equal to the f of x. Okay, so if we do that, so 1 over n is 1 over x because n is x here. Multiplied by partial of m with respect to y is 1 minus x. We have solved it here. 1 minus x minus, okay, minus partial of n with respect to x, which is 1, is equals to f of x. So if we simplify this, 1 over x, 1 minus x minus 1, 1 minus 1 would simply cancel. Okay, that is equivalent to f of x. And that should be 1 over x multiplied by negative x. Or in other words, we have negative x over x, that is negative 1. And that is equivalent to our f of x. Now, if I'm going to ask you, negative 1 is constant, right? So that is our goal, to get a negative or a constant f of x, or to get a constant plus a single variable f of x with x as its variable. So, okay, that's for number 1. So how about, sir, let's try. This is our f of x. How about, sir, for number 2? If we're going to use 1 over m partial of y with respect partial of m with respect to y, okay, minus partial of n with respect to x, okay, is equal to f of y. Okay, so now if we're going to do this 1 over m, our m is simply y minus xy, y minus xy, and we know the result of this already. The result of this is negative x. Okay, the result of this is negative x. Partial of m with minus partial of x. We have seen this. So this should be negative x is equals to f of y. Okay, so if we simplify this, f of y is now equal to negative x over y minus xy. So what is the problem here if we're going to use this as our f of y in our determination of the integrating factor? Okay, so it has two variables in it and we cannot cancel x here. Okay, so we must not use this but rather this one. Okay, and if we're going to use our first formula here, then our formula for the integrating factor if is equal to e raised to f of x dx. So we're going to use this. So this is not okay. Don't use this. Do not use, because it contains two variables x and y. So in our determination of the integrating factor, because we've used the first formula, that is equivalent to, let me just rewrite it again, e raised to the integral of f of x dx. Where our f of x is equal to negative 1. So we simply substitute e integral of the negative 1 dx. Okay? So if we integrate that, we can factor out negative 1 outside of the integral sign. And our result is e raised to negative x. So what is this e raised to negative x? That is the integrating factor. And the integrating factor, when multiplied to our original equation, this DE would be exact. Okay? So what are we going to do? First, let's have the given again. Our given a while ago is y, okay, y minus x to y dx plus x dy. Okay? So this is our non-exact DE. So we have already computed the integrating factor, which is e raised to negative x, so that if I'm going to multiply the integrating factor both sides of the equation, I would make this an exact DE. Okay? So ready to see magic? Yes, let's go. So if I'm going to multiply this should be y minus xy e raised to negative x dx plus x e raised to negative x dy is equals to 0. And furthermore, if I'm going to distribute this e raised to negative x with this, we have y e raised to negative x minus x y e raised to negative x dx plus x e raised to negative x dy is equals now to 0. Okay, we say that we have multiplied the integrating factor e raised to negative, okay, here, e raised to negative x. Okay, so upon multiplying, this would now be our new m, and this would now be our new n. Okay, so let's try to test for its exactness. Partial of m with respect to y is the partial of y of m, which is y e raised to negative x minus x y e raised to negative x. So if we get the partial of this with respect to y and treating x as constant, okay, all of the values that has x as constant, this would be derivative of y is simply 1, which leads us to e raised to negative x minus, okay, x e raised to negative x, and the derivative of y is simply 1. So this is the partial of m with respect to y. Again, if we get the partial of n with respect to x, okay, partial of n with respect to x is, oops, I think you can see, so I will be bringing this down, okay. So let's try here again. Partial of n with respect to x, because that's our condition again when we are trying to solve exact differential equation. Partial of x with respect to our new x. So new n, what is our new n? This x e raised to negative x. So if we try to get the derivative of this with respect to x, this is product rule. Okay? So we need to copy first the first term. And what are we going to do with this? That's right, we differentiate this. Negative e raised to negative x plus, copy this second term, e raised to negative x, and differentiate this first. So that is 1 with respect to x. So as you can see, if I'm going to write this first, e raised to negative x multiplied by this, or what will happen? Minus x e raised to negative x. Is that equal? Is partial of m with respect to y equal to the partial of m with respect to x? Yes, it is. So therefore, our DE now is exact DE, because we have multiplied it with our integrating factor. Okay? So we know now how to solve the DE, exact DE. Okay? Recalling from our previous formula, we have partial of f with respect to x is equal to m of xy. Okay? Partial of f with respect to x is equal now to our new m. What is our new m again? Y e raised to negative x. Okay? Y e raised to negative x. And then we have minus x to y e raised to negative x. So upon cross multiplying that, we have y e raised to negative x minus xy e raised to negative x with respect to x. So if we're going to get the integral of these two, okay, both sides, so remember that f is the solution, okay, to our DE, exact DE now. So we have with respect to x, we can factor out all variables except for x. So we have e raised to negative x, okay, integral, I've applied the properties of integral, minus, okay, y integral of x e raised to negative x dx. So both of these has dx in it, okay, minus, okay. So I've already distributed the dx as well as the integral sign and factoring out the y's here because it is considered as constant because we are only integrating in terms of dx. That's right. So if we're going to integrate this, so what will happen to this? So this would become negative, okay, y because of the negative here, e raised to negative x, okay, minus y times the integral of this. Okay, take note that the integral of x multiplied by e raised to negative x is IDP, integration by parts. So we have to let u equal to x, du with respect to x is simply dx, okay? And our dv is e raised to negative x dx, and our v should be negative e raised to negative x. Okay? So, by the formula of IBP, if you're going to recall, the formula is uv minus integral of the v du. Okay? So, uv, our u times v is negative. This is negative. So, negative x e raised to negative x. Okay? Minus the integral of v. What is v? Negative e raised to negative x. Our du is simply equal to dx. So, if we're going to rewrite that, negative y e raised to negative x minus y, okay, negative x e raised to negative x, if I'm going to factor negative sign here, outside the integral sign, so negative 1 times negative would become positive, the integral of negative x, okay, dx, okay? So what will happen here is negative y e raised to negative x minus y, negative x e raised to negative x. The integral of this, what is the integral of this? That's correct, negative e raised to negative x. So if I'm going to multiply this, negative y e raised to negative x minus, or negative y times negative x would be positive x y e raised to negative x, and negative y times this would be plus y e raised to negative x. Of course, we have the plus q of y. Remember, in exact DE, we have this q of y, of which, because we integrated it in terms of dx, so adding here any function in terms of y would not affect our derivatives. Okay, so that is how we solve the exact DE. So as you can see here, you can see negative y e raised to negative x and plus y e raised to negative x would be cancelled. Okay, so we are left with an answer of x y e raised to negative x plus q of y. And we're not yet done because that is the partial of f with respect to x is equal to mxy. How about the partial of n with respect to y is now equal to the n as a function of xy. Okay, this is pretty easy. Okay, so that's the formula for our exact DE. So, if we're going to do that, again, okay, partial of n is equal now to what is our n? Our new n is this, x times e raised to negative x. So, x times e raised to negative x, I've cross-multiplied this such that this would be dy, and integrating both sides. As you can see here, integrating both sides. So, we have what? F, or I'm sorry, this is partial of f, okay? This should be partial of f because we're doing now the formula for the exact partial of f. So this would be what? So as you can see, this is in terms of dy, so I can factor out x e times e raised to negative x integral of dy. So that's very easy. x e raised to negative x multiplied by y plus r of x. Okay? Function in terms of x because we're integrating with dy. So this should be f is equals to x to y, okay, x to y e raised to negative x plus r of x. And if you're going to equate the two f's here, this f and this f, so we can get the values of q of y and r of x and get the exact d or the solution to our exact de. So what will happen? I'm going to copy this first. X, y, e raised to negative x, this one, because I'm going to equate these two values of f in order for us to get the q of y and r of x. Plus q of y is equal now to the other f, which is xy, e raised to negative x, plus r of x here. Okay? So, this would cancel, obviously, and our value for q of y, there is no variable purely in terms of y on the other side of the equation. This is 0. R of x is still the same. On the other side of the equation, there is no function in terms of purely function in terms of x. So this would be 0. So our answer would be we can pick any of the two f's here. Okay, and add this q of y or r of x here. So I can choose this. So remember that this f would become our constant c, this one. So c is now equal to this one, x, y, e raised to negative x plus r of x, what's the value? 0. Or simply, our solution is c is equal to x, y, e raised to negative x. And furthermore, we can simplify this by bringing down our e raised to negative x as e raised to x. And furthermore, cross-multiplying, we have, let me write this first, x to y is equal now to c e times e raised to x. So this is our solution to the non-exact DE. Okay? Non-exact DE. So we have made the non-exact DE as an exact DE by multiplying the integrating factor. And it is important for us to get the correct integrating factor because that would make our non-exact DE an exact DE. Okay, let's try to have another example for number 2. Solve the non-exact DE 2x to y squared minus 2y dx plus 3x squared y minus 4x dy is equals to 0. And again, first, this is m. This is again our n. Okay? And if we're going to test for its exactness, partial of m with respect to y, or partial of m with respect to y, that's correct. Okay? Partial of y with respect sa m in our m. So we have 2x y squared minus 2y. So if we're going to get the derivative of this with respect to y, making our constant x, okay? So we have 4, okay? 4x y, okay? Minus derivative of y is 2, okay? And get the partial of n with respect to x. So our n is 3x squared y minus 4x. With respect to x, we differentiate this. This is 6x, okay, y minus 4. Okay? Therefore, they are not exact. Not exact. Therefore, not exact. And what are we going to do? First is, again, to subtract this first. Okay? Let's first subtract this. Because our formula is 1 over m partial of y, m with respect to y minus partial of n with respect to x. So if I'm going to subtract this first, partial of m with respect to y minus partial of n with respect to x. Because that is our formula. So what will happen? We have 4xy minus 2 minus 6xy minus 4. So 4xy, distributing the negative side, we have negative 6xy plus 4. So it turns out that this is 4xy minus 6xy, negative 2xy. Minus 2 plus 4 is plus 2. So, here it is. What are we going to use? Is it the first equation or the second equation? Let's try first the first equation. So, our first equation is 1 over m. I'm sorry, 1 over n. This is 1 over n multiplied by the difference that we have used a while ago. Okay? And we know that 1 over n is our 3x squared y minus 4x. So 1 over 3x squared y minus 4x multiplied by the difference of this is actually this, negative 2xy plus 2. So if we are going to multiply that, negative 2xy plus 2 over 3x squared y minus 4x. Can we reduce this into a single variable, f of x? Can we eliminate y here? Okay. So I don't think this would be a problem if we get the integrating factor. Okay. So because we cannot actually express this in terms of our simple x, or we can use this still. I'm sorry, not. We cannot use this because we cannot express this simply in terms of a single variable and a constant. But if we're going to use 1 over m, partial of m with respect to y minus partial of n with respect to x, as you can see, 1 over m is 2xy squared minus 2y. 2xy squared minus 2y multiplied by negative 2xy plus 2. So if we are going to continue that, so we have negative 2xy plus 2 over, okay, here we can factor out negative y. So if we factor out negative y here, our answer would be minus 2xy, okay, plus 2. Such that we are able to cancel this. And we are left with what? Negative 1 over y. And this is our, again, from our formula, this is our f of y. So if we use that as our f of y, okay, if we use this, our integrating factor formula, again, if we're going to recall, is e raised to negative integral of f of y dy. Okay? So what will happen? Integrating factor, we're going to solve that. Negative integral of f of y, negative 1 over y dy, of which we can factor out negative outside of the integral sign. So negative times negative, that should be simple. This would be dy over y. This becomes positive. Okay? And it's simple, e raised to ln of y. And by properties of ln, oops, let me just rewrite this. And by properties of ln, e raised to ln, we can cancel that and we have an integrating factor of y. Okay? What do we do again on our integrating factor? Okay? We would multiply this integrating factor into our whole equation. Our equation or differential equation is 2xy squared minus 2y dx, okay, plus 3x squared y, okay, minus 4x dx. We are going to multiply this by our integrating factor, which is y. Okay? I'm sorry, this is equal to 0. Okay, this is equal to 0. Multiply it by y. So what will happen is that we will be having 2xy cubed minus 2y squared dx plus we have 3x squared y squared minus 4xy. Of course, this is dy. I'm so sorry. This is dy. Okay, dy is equals to 0. Okay, so again, this is our new m. This is our new n. If we're going to get or test for its exactness, because we believe that if we multiply the integrating factor, the correct integrating factor, so we would be arriving at an exact dE. So we're going to get the partial of this with respect to y. Okay. With respect to y, we have 3 times 2 is 6. 6xy squared. With respect to y, this is minus 4y. Okay? Then partial of n with respect to x is this. Going to the right, this is our n. 3x squared y squared minus 4xy. That should be with respect to x, that is 6xy squared with respect to x, power rule. And with respect to x, this is minus, derivative of x is simply 1, so minus 4y. Therefore, they are exact. And we know how to solve exact DE. So in order for us to solve exact DE, we have partial of f with respect to y, or with respect to x first. Okay? With respect to x. So we have partial of f with respect to x is equal to m as a function of x, y, or simple x or y. So we have partial of f is equal now to our new m. Our new m is this, okay? 2xy cubed minus 2y squared with respect to x. So if we're going to integrate this, both sides, so we have f is equals to, I'm going to distribute the integral sign. We have 2xy cubed dx minus the integral of 2y squared dx. Okay? Since this is with respect to dx, I can factor out any variable other than x because it is considered as constant. As well as the constant, real numbers I can factor out outside of the integral sign. So we have 2y cubed integral of x dx minus 2y squared integral of dx here. If I'm going to integrate this, 2y cubed, this should be x squared over 2 minus 2, integral of dx is simply x. So 2xy squared, okay, plus q of y. Okay, so this would cancel. So we are left with x squared y cubed minus 2xy squared plus q of y. Okay, plus q of y. Okay. And another thing, we're going to solve for the partial of f. Partial of f with respect to our x. Okay? So, of the n xy. So, we have 3x squared minus 4xy. 3x squared y squared minus 4xy. Okay? Let me just check again. Then, with respect to, this is with respect to y. So, integrating both sides of the equation, we now have f is equals to the integral of 3x squared y squared dy minus the integral of 4xy dy. So, this is with respect to y. So, all of the variables is just for y, I can factor out. Same as the constants. So, we have 3x squared integral of y squared dy minus, I can factor out 4x outside of the integral, and we are left with y dy here. So, integrating 3x squared, we have y cubed over 3 minus 4x y squared over 2 plus r of x. Okay? So, this would cancel. This would cancel. So, we have 2 here. So, we have x squared y cubed minus 2y squared plus r of x. Okay? So, that is our other f. So, if we're going to equate our f here and our other f here, that should be x squared y cubed minus 2xy squared plus q of y. Again, we're equating in order for us to get the value of r of x and q of y. So, x squared y cubed minus 2y squared plus r of x. As you can see here, class, that this would cancel. Okay? This also would cancel. Oh, of course. I'm sorry. This has an x here. Okay? 2xy squared. So, this is 2xy squared. I'm so sorry. I forgot to write that. So, 2xy squared. So, we have x here. 2xy squared. So, let me just rewrite this here. 2xy squared. Okay? So, such that these two also would cancel. So, this should cancel. And we are left with the value of q of y. On the other side, there are no purely in terms of y. So, we have 0. R of x is 0 also. And we have already the answer. We can choose any of this f or this f for us to get the answer. So I'm going to choose this. So our f would simply be replaced by c. This should be x squared or y cubed minus 2xy squared plus 0 because the value of q of y is 0. If you're going to choose this also, you will still be arriving at the same answer. So our answer would be x squared y, let me just rewrite, x squared y cubed minus 2xy squared is equal to c. Okay? And this is our solution to our non-exact DE. Okay? So, I'll give you an exercise. So, if you comment down below our correct answer, I'll be checking it. Okay? So, let me give you another problem. Okay? Our problem for you to answer is we have xy dx, okay, plus 2x squared plus 3y squared minus 20 dy is equals to 0. Okay, and you can comment down it below if you have the time to solve this, and I will be giving the answers most probably if someone or if this video gets a 1K views. So, I hope you learned something for today for solving non-exact DE and making it into an exact DE by multiplying of what we call the integrating factor. Okay? So, thank you so much for listening. Have a nice day and God bless you.